at this point we know all about equilibrium constants and how to set up equilibrium constant expressions, such as shown down here. So for any reaction you should be able to do that, and there's actually a for gaseous reactions where all the reactants and products are in forms of a gas, you can also express the equilibrium constant in pressures or partial pressures, and that's goes back to the gas laws when we learned that first semester, that if you have a mixture of gases, if you remember, at a standard temperature and pressure, any gas, ideal gas, will occupy the same volume, 22.4 liters for a mole, and that means that independent of the molar mass, that the mole fraction is going to be equal to the pressure fraction. So if you have the partial pressure in a mixture of oxygen and you divide it by the total pressure of the gas mixture, that's going to be equal to the mole fraction of oxygen divided by the total number of moles in the mixture. And so this is how we can come up with Kp and Kc and express equilibrium constant that way. So those two are not necessarily the same. They only are if the total volume doesn't change, because molarity, of course, is number of moles per liter, and the pressure fraction would be an ATM, let's say ATM of O2 divided by the total pressure, and if you have a change in total number of moles, then your volume will also change, and so that means that the concentrations are different from the mole fractions. And so we use this equation here, the Kp, the equilibrium constant with pressures, equals Kc times RT ideal gas constant. I will give you this equation times the temperature in Kelvin and times delta N, which is the change in the number of moles, right? So if you go, for example, in this reaction down here, if you have 2 moles total and your product also has 2 moles, then Kc is going to be equal to Kp. Those two are equal. But if you are changing the number of moles, then your mole fraction, your pressure fraction changes, and so then concentrations and pressures are different. But it's a pretty easy calculation. And so that's only if delta N is equal to 0, right? So that makes RT to the 0 power is 1, so then Kp is equal to Kc. So if I gave you this reaction here, find Kc for the reaction 2NO and O2 goes to 2NO. So here we have 3 moles going to 2 moles. So delta N is going to be -1. Right? If it was the reverse, it would be +1. We go from 3 moles to 2 moles. That's a change in -1 mole. And we're provided with Kp, so then simply Kc would be equal to Kp divided by RT to the delta N. Kp is 2.2 times 10 to the 12. Divided by the ideal gas constant, 0.08206 liters, atmospheres, moles, and Kelvin, times K, temperature in Kelvin, so that's 273, plus 25, which is 298 K, times 298 K, and then of course to the -1 power, which is what delta N is, and so we get a number of 5.4 times 10 to the 13. That would be Kc, so they're not the same. Alright, so don't want to work a whole lot of problems there, just a conceptual question here, right? So for which reaction is Kp equal to Kc? So all you're doing is you're looking at the number of moles of the reactant side and the product side, and of course only look at gases. So for A here, that doesn't count. So we have 2 moles here going to 1 mole. Again, that solid doesn't count. So Kc is not going to be equal to Kp because we have a -1 change in number of moles. So what we're looking for is where delta N is equal to 0. For this one here, we again take out the solids, and so we have 3 moles going to 3 moles of gases. So this one would be Kc would be equal to Kp. And just to make sure, here we have a solid, so no gases on the left. We're producing 2 moles of gases, so we would have a +2 delta N, and therefore Kc would not be equal to Kp. Cranking things up, making things more complicated. Let's use the equilibrium constants and see if we can relate and calculate concentrations of reactants and products at equilibrium. So, consider the reaction: carbon monoxide and hydrogen gas forming methanol. We already saw this reaction. It has an equilibrium constant. We don't know what that is, but we are told that a reaction mixture at 780 degrees, and we're keeping that constant, initially had a concentration of 0.5 molar, and the hydrogen gas, those are the 2 reactants, had a concentration of 1 molar. And at equilibrium, the carbon monoxide went from 0.5 to 0.5. And so we set up these so-called ICE tables. That's what we call them, ICE. Initial concentrations of reactants and products, then there's going to be some sort of shift or change, and then we can calculate the equilibrium concentrations. And so what we use to do that are just the balanced stoichiometry factors, right? Because we know there's 1 mole of carbon monoxide reacting with 2 moles of hydrogen gas forming 1 mole of methanol. And that's important because we know that for every 1 mole of carbon monoxide that reacts, we need to consume 2 moles of hydrogen, and then 1 mole is produced. So we're told that at the equilibrium concentration is 0.15. What we don't know are the rest of these here. But we know that the change is related. So if it goes from 0.5 molar to 0.15 molar, we know it went down by 0.35. So you'll set these ICE tables up, and then once we have that, we can just simply plug it into, for Kc here, what is the equilibrium constant? Yeah, we'll do, so it'll be methanol over concentration of carbon monoxide times the concentration of hydrogen gas squared. We already know what CO is, so that we can plug in. It's 0.15. Alright, so if this goes down by 0.35, we need twice as much, so 2 times 0.35 to disappear. Again, that's from this relationship here. So that's going to be minus 0.70. So what's left over at equilibrium here is 0.30 molar. And then this was at 0 initially, so it's going to go up by a factor of 0.35. So this goes up by 0.035. And so this is 0.35. Now we can plug it all in. So 0.35, this is M if you wish. And then it is the hydrogen concentration, 0.30 squared. And when I calculate that, it's going to give me an equilibrium constant of 26. So it's not that hard. We call these ICE tables. Now let's do one more. In fact, we're going to do a whole bunch of them. Let's do one without the little guidance here. So we have a reaction of methane gas forming ethylene and hydrogen gas here. And we are told that a reaction mixture at 1700 degrees initially contains 0.115 molar methane. That's our reactant. And at equilibrium, the mixture contains 0.035 m of one of the products. So I would always write the reaction above CH4 and keep that in there, the stoichiometry, since it's important. C2, H2, and 3H2. And so you can turn this into an ice table, ICE. We know that the initial concentration of methane is 0.115, and then we are told then this is 0 and 0 initially, right? Because we're not, that's, the reactant is methane and there's nothing else there, but we are told that at equilibrium the concentration then is 0.035 m. Alright, so that means it went from 0 to 0.35 m, so we know this went up. So the change was 0.035. From there we can get all of the concentrations, because we know hydrogen needs to go up 3 times as much, so that's going to go up by 0.105. And here we have, this will go down by, or this will go away by 0, twice of this factor here, right? So if we call this the factor x, that's going to go up or down by 0.070. So if I subtract that from 0.115, I get 0.045. This we already know. This goes to plus 0.105, and then we can plug it into Kc, which equals 0.105 cubed times 0.035 divided by 0.045 to the second power, and that gives me an equilibrium constant of 0.020. When we come back, we're going to complicate things as always. We're going to set up some ice tables.